The orbit of Earth about the sun is almost circular. Assume that the orbit is a circle with radius 93 million miles. Its angular and linear speeds are used in designing solar power facilities. Okay, that's interesting. We're thinking about, so for this question, we're looking at the orbit of Earth around the sun, which is technically very close to elliptical, or like very close to being elliptical, but you can make an approximating assumption that it's circular, and that's what we're going to do here. So they're referring to its linear speed, which is just its velocity. It's change in position with respect to time, right? Its velocity. But then they're also talking about its angular speed, so the rate of change of the angle, this angle, omega. And so this velocity here, its actual speed and also its angular speed are used in designing solar power facilities. So that's interesting. Okay, but for this problem, we're going to use the simplifying assumption that it's follows a circular orbit, with the circle having radius 93 million miles, which we can still probably get some pretty accurate answers doing this, right? So if you think about the actual ellipse, maybe 93 million miles is like the average of you take the minor axis and the major axis length and average those two, and perhaps that's 93 million miles. So still get some pretty accurate answers here. Assume that a year is 365 days and find the angle formed by Earth's movement in 1 day. Okay, so we're assuming that the angular velocity of the Earth is constant, and I'm sure that's a really good assumption, right? It's not like the Earth, when it's coming around the one part of the sun, it's going faster than in other parts. And so they're just saying that, we don't know where it's not like we have to start from here. Like, it could be anywhere. Just we Earth's at one spot, okay, and then so it's at that one spot, and then 1 day later. So maybe here's the first spot, and so 1 day later, how far has it moved in terms of angle? Assuming that a full rotation is 365 days. Well, if you think about it, so we can just use like proportions. So okay, we're thinking about 1 over 365. This fraction of a full rotation is what we're thinking about, right? The Earth goes one full rotation in 365 days. So it's this fraction of a full rotation. But what's a full rotation? 360 or 2 pi, whatever. So it's this many degrees. (72 over 73), about 0.986 degrees, almost 1 degree. And I'm going to leave that in degrees. So 0.986 degrees. All right, give the angular speed in radians per hour. Okay, well, we can, if we've got, so let me write a couple more digits here. So if it's 0.986301, this is degrees per what? Per day. The Earth moves this many degrees in a day. Okay, so we've got everything we need to get, this isn't, it seems weird, but this is an angular velocity right here. 0.986301 degrees per day, that is an angular velocity. It's an amount of angle per an amount of time. That is angular velocity. It's just, it's not in units we're used to expressing angular velocity in. So all we have to do here is just do a unit conversion to the units that we want. Okay, because again, it's not like the Earth is going to have a different angular velocity at some other position around the sun. We're assuming the angular velocity is constant. So if we know the Earth moves a certain amount of angle in a certain amount of time, then we've got the angular velocity. We just need to convert that to what we want, which is radians per hour. So, okay, how do we convert degrees to radians? Well, we worked a whole section on doing this. There's pi radians for every 180 degrees. So degrees cancel. There we go. So now we're in radians. Now we have the angular velocity in radians per day. How do we convert days to hours? Well, that's easy. We know that there's 24 hours in one day. Days cancel. So there's radians per, we're left with radians per hour. That's it. So this is part B we're working on here. So there's 0.986 times pi divided by 180 divided by 24. Okay, 0.000717 radians per hour. Okay. All right, find the approximate linear speed of Earth in miles per hour. So there's that term linear speed. I don't like saying linear. They're saying that it's, change in position with respect to time, actually going along the circular path, which is going to be constant because since the angular velocity is constant, we know that with circular motion, that means that the actual velocity is constant as well. So, okay, we can use the formula V is equal to omega R, and we want miles per hour, so we'll stay in hours. All right, so 0.000717 per hour. We won't put the radian units. Okay, and then, well, let's do this. We'll go ahead and do the conversion right now. So now we've got, we won't even have to do a conversion. So we're already in miles, 93 million miles. And so, yeah, that's miles per hour. So this times 93 million, 66,705 miles per hour. Okay, so now we're going to look at Earth from the perspective of rotating about its own axis. Earth revolves on its own axis once every 24 hours. Assume that Earth's radius is 6,400 kilometers. Find the following. The angular speed of Earth in radians per hour. So we can think about, the Earth is a sphere. And so it's rotating about, an axis like this. But we can view the rotation from the perspective of just uniform circular motion. If we think about, like let's think of maybe the equator. I know it's actually in actuality rotating about like a tilted axis, but still, I guess if you look straight down at where it's rotating about, you could think about a circle there, and with that circle, we can do the whole angular velocity uniform circular motion problem. Right, so here's this, arc length. Here's the radius of the Earth. Right, the surface of the Earth has a certain velocity. So when you think about it from that perspective, we can view this from the uniform circular motion problem, everything we've learned in this section, with the variables v, s, omega, time, theta, etc. Okay, so the angular speed of Earth in radians per hour, what is omega? Okay, well, let's see. Well, what information does it give us? It gives us the radius. We have the radius of the Earth. So we know R. Okay, and it tells us that Earth revolves on its axis once every 24 hours. So that is omega. We have its angular velocity. We have a certain amount of angle over a certain amount of time. We have its one revolution, so it goes all the way around 2 pi radians, 360 degrees, in 24 hours. Right? A angle amount per time. But now we just need to convert this to what it's asking, and we're already in hours, so we just need to say that convert revolutions to radians. Well, there's 2 pi radians for every 1 revolution. So now we're in radians per hour. So we've got, let's see, 12. So yeah, it's pi over 12. Okay, what is the linear speed at the north or south pole? Okay, well, I don't know the specifics of how the Earth rotates, but to me, if we're viewing the axis of rotation as passing directly through the north or south pole, then the linear speed is 0. And why is that? Because, okay, we do the whole derivation and we get that V is R omega, right? Well, if you're at the north or south pole relative to this circle here, what's your radius? It's 0, right? So 0 times omega is 0. Again, I don't know the specifics of how the Earth is, where the axis of rotation of the Earth passes through. I guess they're saying it goes through the north and south pole. But you can think about those. So like these are the latitude circles, like the equator circle is a latitude circle. But you're going to have different circles. Like there's different radius latitude circles. The longitude circles are all the same diameter or radius. But the rotation of the Earth is with respect to the latitude direction, not the longitude. And so your speed, like velocity based on the Earth's spin, is going to be different depending on where you're at from a latitude perspective. So, but no matter what, the concept is still the same. The concept of, you can boil it down to uniform circular motion. And what you can think about though is no matter what latitude you're at, you're going to have the same exact angular velocity no matter what. Okay, so in part C it says, what about at a city on the equator? Well, what's the R in that case? The R is the radius of the latitude circle that you're at. The R in that case is going to be the radius of the Earth. When they say the radius of the Earth, they're referring to like the radius of it's like the radius of the sphere, which is going to be either the equator circle or any of the longitude circles, right? There's a longitude circle. Here's another longitude circle. That's what they're referring to when you say it's the radius of the sphere itself. So that's going to be at the equator, and so that corresponds to Earth's radius. So in that case, V is R. They want this in, they don't tell us, so we'll just do kilometers per hour, 6,400 kilometers, and then pi over 12. Radians are unitless, so that's going to be kilometers per hour. So let me this is 0 kilometers per hour. And then 6,400 divided by 12 times pi. Okay. 1,676. Okay. All right, interesting. Okay, part D, approximate the linear speed. What is the approximate linear speed at Salem, Oregon, halfway from the equator to the North Pole? Yeah, so what they're going for here is, okay, you're here, right? So you're going to have, it's going to be V is equal to R omega, but R is going to be whatever the latitude circle halfway up is. Halfway from the North Pole or from the equator to the North Pole. And to actually get this radius, we'd have to look at so you'd have to take, I'm just going to say it's half of, I'm going to say it's half of this here. So 6,400 divided by 2, that's what we're going to use. However, I don't want to make this video too long, but if we want it to be more accurate, we would take the equation of a circle of radius 6,400 kilometers, right? x, y. So we have the equation of a circle that's 6,400 kilometers, and we would find the x coordinate. So okay, this is 6,400, this distance, right? So 6,400 divided by 2 is 3,200. So we would find here would be 3,200. What is this x coordinate? I mean, we could do that. Let's do that. We can do that real quick. So, okay. All right. So we've got a circle here on an XY plane. It's centered at the origin. What is the equation of a circle centered at the origin? It's x squared plus y squared is equal to r squared. So what is 6,400 squared? $4,096 and then 4 zeros. Okay, so that's the equation for like any longitude circle you can think about. And so what we're thinking about is the latitude circles are going to have radius equal to, like, that's going to be at this distance away from the equator. The latitude circle is going to have this radius. So what we want to think about, we want to set y equal to 3,200 and then solve for x. That's what we want to do. So we've got 30, or x squared is, and we can subtract y squared from both sides, minus, and then this is going to be 3,200 squared. Okay, so this minus 3,200 squared. Okay, now let's take the square root. 3,200 root 3. And we don't need to think about plus or minus. All the plus or minus using the square root property, it's because it's saying that at this y you've got two x values, this one and this one, but let's just think about the positive one, doesn't matter. So 3,200 root 3. And that is the radius that corresponds to being in Salem, Oregon. So you see it's a little bit different, right? It's not quite 6,400 divided by 2. So, okay, 3,200 root 3 kilometers. And then the angular velocity doesn't change. It's pi over 12. So there you go. In kilometers per hour, we have, so 3,200 root 3 divided by 12 times pi 1,451.